Welcome everyone to today's webinar. It's a great pleasure for me to introduce the speaker, Peter Zhang from Carnegie Mellon University. So Peter is an assistant professor at Carnegie Mellon University's Haynes College of Information Systems and Public Policy. He earned his PhD from MIT, the Engineering Systems Department, and specialized in optimization, robust decision making, and data-driven analytics with application to supply chain transformation. And he has many publications, including the publication OR in management, in mathematical programming, transportation research, just to name a few. He was also the recipient of the Informed Junior Faculty Paper Competition Award, Kopman Prize, the Wagner Prize, among others. So it's a pleasure having you here, Peter. And without further ado, I want to give the control of the screen and the mic to you.
All right, thank you very much, Reza and Yanis, for having me here, and thank you everyone for being online here, or if you're watching the recording, thank you for watching. So this is a joint work with my PhD student, Hao, who is on the call right now as well. It's called Robust Path. So we work on this. Basically, think about the parametric programming version of robust optimization, or in other words, the hyperparameter choice or selection problem in robust optimization in a specific way. Okay, so go ahead. So Hao is a fifth-year student at Heinz, and we will look at what we did in this paper. So in robust optimization, as we commonly know, there's sometimes a practical consideration of how to choose the uncertainty set, or how to choose the hyperparameters for the uncertainty set, and that involves the different types of constraints that we can include to specify the uncertainty set, or that would dictate the shape as well as the size of the uncertainty set, and how many uncertain scenarios do we want to include, and how conservative we want to be as a consequence. So we will focus on a specific parameter, the radius parameter, basically the size of the uncertainty set for this talk. But just want to quickly mention that the general idea of hyperparameter selection is not unique in robust optimization, and it's also not the first time we look at this problem, right? So in portfolio optimization, which can be thought of as a cousin of robust optimization, or in regularized learning problems, and other application areas, there's usually the similar question of how to select one or several hyperparameters that would reflect the right balance between the modelers or the decision makers' goals. And so in order to choose the hyperparameter values in a way that is useful in practice, typically one needs to solve the robust optimization problem or the corresponding problem many times, each corresponding to one hyperparameter setup. And this approach may work in some cases, but may not work in some other cases. Right? So, for example, it may break down computationally in practice if the allowable time to solve these n different instances of the same problem is shorter than is too short compared with the actual solution time of one instance. For example, in autonomous driving, if the vehicle needs to dynamically adjust the robustness of the driving policy on the fly, then that decision has to be made within 10 to 100 microseconds, um, which is pretty fast. If and probably infeasible if we need to sweep through many different solutions by solving them different times with different hyperparameter setups. And another aspect of the approach of just manually solve the problem many times is that there's really not enough intuition for us to understand what is happening underneath, right, in terms of the relationship between the solutions or the performance of those corresponding solutions when we vary the hyperparameter values. And the very brief, non-exhaustive literature on the hyperparameter selection, and starting with the robust optimization context. In the Price of Robustness paper from Dimitri and Melvin, they talked about the coverage or the trade-off, right, between how much we want to be conservative, and by Tim Chen and Phil Marr, they had a paper that talked about a similar problem of how the solutions would change if we change a radius parameter of the uncertainty set in robust optimization. And there they described some mathematical properties of the solution set that can be derived from the varying values of radius. And then more recently, we have seen papers again talking about learning or obtaining the solution path, optimal solution path, when changing the hyperparameter values in regularized learning problem, in stochastic programming problems. And beyond optimization in finance, there's a well-known two-font separation theorem that talks about basically to generate the Pareto frontier of portfolios to balance or trade off risk versus return. You can use a risk-free uncertainty set, and if I remember correctly, a risk-free portfolio, which is maybe in some case cash, and plus another risky asset, and the two of them would be sufficient to construct the Pareto frontier to trace between high risk and high return scenarios or portfolios. And there's some many different work after that. And in statistics, so regularized path is a known concept, is a well-known concept. For example, in 2004, in Annals of Stats, they discussed the approach to obtain the regularization path or the solution path by varying the regularization strength hyperparameter, which mirrors what we are doing here of varying the uncertainty set radius. And they talk about the shape and then the algorithm of doing that in a specific problem setting. And of course, in general, the very general understanding of this kind of problem is that this is a specific case of parametric programming problems. And I'm not an expert in that, and so I won't dive into the literature. Okay, sorry, 1 second. So the setup for the majority of the talk today is that we're going to be looking at this particular form of the problem. It's not the most general robust optimization problem. This is what I want to emphasize, but it does generalize quite a bit later on. Okay, but so for the sake of discussion, let's focus on this very clean, simple setup where we're minimizing, so X is our decision variable, A is our uncertain parameter, chosen by the adversary from the uncertainty set U, and U is parameterized by the radius R. I'm going to talk about how that happens exactly. But the objective function is linear. It's linear in both in A and also in X. And the feasible region X, we assume it is smooth and strictly convex. And importantly, there is no uncertainty in the uncertainty set, in the feasible region. So which means that the constraints of the problem are deterministic constraints. They are not uncertain constraints. And that is probably one of the few assumptions that we cannot relax in this work. And the uncertainty set is written as follows. We assume it is centered at A0, right? Centered at A0, and it can grow outward in the shape of the set defined by B. It's given to us. And then the radius, the size of the growth, is determined by the radius R. In other words, every element in this uncertainty set can be seen as a combination or the sum of the A naught center plus the radius times some perturbation B, where B is drawn from this fixed shape or fixed convex compact set B. So A0 and A naught and B are both given to us. So we assume that we know the nominal value and we know the shape, or we want to keep the shape and only grow the radius. Okay, so what does this mean in general? So objective function is linear in A and in X. We eventually could relax this to be more general objective function that is concave in A and convex in X. Right, so that's so we feel reasonably happy about that. And the assumption about here, the setup about X being smooth and strictly convex, this is a technical assumption that we need to make the analysis simpler, technically simpler, and we believe we can relax this as well. The deterministic feasible region setup, this part we cannot relax at the moment. So we only have uncertainty in the objective function. Uncertainty set, so what does UR include or not include? Right? So this could include sort of arbitrarily shaped compact convex set in with a center with an anchor point A naught. But importantly, it does not cover the case of the famous budgeted uncertainty set from Dimitri and Melvin's work. Right? For example, if we have L1 and then L infinity intersection, and then by changing the budget gamma, we can change the size of the uncertainty set, but not in the way of scaling the uncertainty set uniformly in different directions. So this budgeted set is not going to be covered by our method or by our analysis here. Okay, so good. So with that setup, now let's look at what we do. So our goal is to identify, under this setup, identify the menu or the set of robust solutions when varying the radius parameter, hyperparameter. And the outcome is that we do actually discover an approach to approximate multiple robust solutions, and only in two different solving passes, right? Only solving the problem twice instead of n times or many times. And under some conditions, the approximate algorithm that we propose is actually exact in recovering the set of robust solutions, or I should say recovering a subset of the continuum of the robust solutions from continuously varying R. And we run some numerical experiments. Okay, so the problem setup again, if I talk to my um, first year students who are taking our course, we would set up a problem like this, minimizing objective function by choosing x subject to uncertainty in the parameter a. And the first thing that we can do is that how do we deal with the uncertainty in a? Well, the first thing is we can ignore it. Right? So maybe we can ignore the uncertainty and just try to solve it. We can call this solution you can call them any different ways. So you can call this, but let's define this as the efficient solution, assuming uniqueness for our simplicity. So assume this is a unique solution, and that holds under our current assumption about the feasible region and the problem setup. So we have the efficient solution being the optimal solution for the nominal value a naught. And but if we do want to truthfully consider uncertainty of a, we can write an robust optimization problem. Um, or distribution robust or stochastic, but let's say we write the robust optimization version, and we consider A to be drawn by an adversary from the uncertainty set U, and the robust optimization is the typical one here that has uncertainty in the objective function, and we can define the robust solution with this large uncertainty set, assuming U is the largest one that we care about, plausibly. So capital R, XR is defined as the robust solution, assuming uniqueness under our assumption. R is the robust optimal solution for the optimization of this objective under the uncertainty being drawn from the large uncertainty set U here. Okay, so given the two different X solutions, they of course would perform differently under different measures. And there are many different different metrics we can compare them under. Let's say, for example, we consider two um, types of metrics. These are not the only metrics that we should or we can compare them under. But for illustrative purpose, let me use these two metrics. The first one is we can call that efficiency. Efficiency is for the efficiency of any solution X. We define that as the performance of that solution X under the nominal value A naught. Simple enough. And then for another metric could be robustness, where we define the robustness of a solution X to be the worst case performance of X, where we can draw A from the large uncertainty set U here. So by design, because the efficient solution is obtained from considering A naught alone, so that's going to be the optimal solution. That's going to be the best performer for the efficiency metric. And conversely, by design, the robust solution is the one that is obtained from choosing A from the largest uncertainty set U, and that is going to be the best performing solution for the robustness metric that we defined here. So that is to say that efficient solution is better than the efficiency of the robust solution or efficiency of any other solution, and the robustness of the robust solution is weakly better than the robustness of the efficient solution and the robustness of any other solutions. So, but again, these are the two sample metrics that we can use to illustrate what we do here. So then in the same sort of a two-dimensional metric space, measuring the efficiency of a solution and measuring the robustness of the solution, these two solutions, XE and XR, they occupy two different points, right, on the space, right, two opposing points. And so presumably, when we change the uncertainty set size, we're going to trace some kind of curve in this two metric space. two objective space. And here we are thinking about changing the uncertainty set by shrinking the R value, which is basically saying U is going to be still always anchored around at A0, and we're only shrinking the R value, but keeping the shape the same. Um, okay, so and not hard to see that as we have smaller and smaller uncertainty set, here we smaller and smaller uncertainty set, we tend to we tend to expect the performance of the uncertainty set to be increasing in efficiency metric and decreasing in the robustness metric. Yeah. Okay, so that's sort of, and this is illustrative. I don't think so. This is in general mathematically not precise, but this is illustrative for our purpose. Not precise in the following sense. Right? So a couple of things. One is that this solution path visualized in the performance space, in the efficiency and robustness space, right? Um, uh, Recall that this is not the solution space. This is not the decision space. This is some arbitrary space that we just created for visualization. Um, the path here is not the best or is not the Pareto frontier in general, meaning that it's possible that we can choose other solutions from the same feasible region X that could dominate some of the points along this path. Right? That is entirely possible. Um, uh, or in other words, this robust path as manifested in this objective space may not be the actual Pareto optimal frontier for the two metrics, for the two objectives, efficiency and robustness. Um, but they do coincide if the objective function is linear in A, and that is the setting we are talking about. Um, and so for convenience, this is what I use here. And I use this bi-objective space for illustrative purpose. And but the theoretical results, the concrete results from the paper, do not really rely on any analysis of whether the robust frontier is the same as the Pareto frontier, right? The analysis in the paper is more about directly comparing the robust solutions um, in the solution space, in the decision space. Okay. But so with that sort of caveat aside, I want to just come back here again. So to say that, yes, we can try to understand, compare the different robust solutions, or we can try to obtain the different robust solutions by solving them multiple times. If we need n of them, we can solve n times, each time with their corresponding radius or corresponding uncertainty set size. That's the simple traditional manual approach. And in the case of our work, our paper here, we propose something different in order to obtain a subset or a subset of the robust solutions. Okay, so oops, okay, so our approach is basically the following. So first of all, we solve the most robust problem, which is to basically the XR solution. And we can keep track of it. We use it. You can think of it in two different spaces. One in the objective space, the other one maybe in the actual solution space. You have some XR, but it's probably more accurate to think in the solution space. So you have the XR as a starting point. You use that as a starting point for an optimization algorithm, and the algorithm would be solving not the robust solution anymore. The algorithm, because we already solved it, we start from the XR, the most robust solution, and we use that as a starting point to solve for the nominal problem with only a knot, no uncertainty. So and this and the solution procedure is not precisely speaking, is not the usual gradient descent. But we can think of it as a variant of gradient descent, right? It's going to be a customized version of proximal point method, which is basically at every step, means that at every step of the optimization algorithm update, we want to go from the previous update in the direction that is minimizing the objective function the fastest, right? The usual gradient descent kind of flavor, but not going too far away from the previous update. Right? So that's the proximal concept. And that far away requires a measure of divergence or distance. And that measure has a precise construction based on the shape of the uncertainty set. So it's not free lunch and there's no magic there. We used uncertainty set shape to construct a proximal measure, Bragman divergence, and then we use that to run a proximal point algorithm, starting from XR and iteratively going forward, always solving for the nominal problem. And we claim that along the way, we can collect the intermediate solution iterates, and they are close to or they can approximate the robust solutions. Here, I should probably be more precise here that this is we shouldn't say Pareto efficient, but we can approximate robust solutions. Okay. And that's the entire algorithm. Right? So we start from XR. So we solve the problem once, solve the most robust problem, and obtain XR. And we solve the problem a second time, that is solving the nominal problem, using the proximal point algorithm updates customized by the uncertainty set. And that's the only, so we only do two different solves. And along the way, for the second solve, we collect the intermediate solutions, and they correspond to or they approximate our robust solutions that would have come from solving the problem individually many times by varying the radius value. Okay. Okay. So then go forward. Okay. Good. All right. So the intuition of that is that of how the two different solution sets are actually related or can be related is the following. So imagine we have let's say we have a robust optimization problem as we discussed that is linear in the uncertain parameter A in objective. If we can write it, if, for example, if U is a ellipsoidal uncertainty set defined by some covariance metric like parameter sigma, then we can take that sigma and then put it in the regularization term. So we can write the regularization version of the optimization problem due to the linearity in A. And so that is well known. And then but then this can be trivially converted to the next line. That is, the regularization on X is the same as regularization on X minus 0. Okay. There's some typo here. This should be just the same R in the two different lines. So basically, having the different RK values, for example, we would be obtaining different solutions that correspond to different regularization strength, or equivalently different robust strength here. And so that's one way to understand to represent the robust optimization formulation. On the proximal side, the proximal algorithm updates is essentially doing the following thing every time. Right? So it is first optimizing minimizing the nominal objective, a naught times x. Every iterate, every step you update from xk minus 1 to xk. But it's minimizing not only the nominal objective, but the nominal objective plus some penalty to prevent the next iterate xk to be deviating too far away from the previous iterate xk minus 1. So there's a penalty there. So there's step size or some penalty lambda times the x minus xk minus 1. I'm choosing the right x to be the next iterate xk. And these two forms are somewhat similar in the sense that they are both solving similar objective functions, but one is anchoring the solution at 0 always. The other one is anchoring x at a moving target, the previous iterate of the optimization algorithm. So they're not the same. But sometimes they can be quite close. So here's an intuition about one of them. So in this setup, let's just consider x to be drawn from the entire space. There's no constraint on x to simplify our story. The robust optimization problem is to solve this thing, this objective function, regularized objective function, where the nominal value appears in the first term, and then the ensemble set size appears in the regularization strength for the second term, for the penalty. Imagine what happens with r equals infinity, positive infinity. Right? If r is extremely large, that basically means that the second term dominates, and so the difference between x and 0, or the norm of x minus 0, if we want to minimize that, we basically should probably keep x at 0 exactly. So then we don't deviate away from the most robust solution, or we don't deviate away from 0. Now, as we change the value of r, as we relax, as we decrease the value of r, we then are putting less and less emphasis on the penalty, on the anchoring of x onto 0, right? So we are allowed to go further and further away from 0. And that distance of further away, let's say in this case we measure by the Euclidean norm, that distance of going away is equally far in all directions, right? So basically the circles would represent the equal distance, concentric circles representing the equal distance or equal norm values for x. So then which direction do we go along one circle? Well, we want to go in the minus a naught direction. A naught is pointing up, so we want to go into the downward direction in this case. So that is minimizing a naught times x, subject to the bound, or not the bound, but then the proximity penalty between x and the origin, 0 here. And as we decrease the value of r, we can stray further and further away down to be better and better in the minimizing a naught times x objective. So that's in a very simple case. That's a very simple solution path from a sequence of robust optimization problems with different radius values. Okay. Now, in a proximal case, the first solution would be the same, because we initialize our solution algorithm at the most robust solution, which happens to be, we already showed that it is the origin in this case. So we start from that same origin, we'll call that x0. And from there, we do the following. So we minimize the composite objective function of a naught times x plus a penalized distance between the next iterate and the previous iterate x0. So how do I measure the distance from x0 to the to other points, right? We basically draw a circle around x0, and any point along this circle has the same distance, so it's equally penalized as a distance away from x0. But because we are choosing again the minimizing x naught times x direction, so we want to go down in the go in the opposite direction of a naught, and that is going down. So we would then, based on the this first step, we would go to x1. And the next step, when we optimize for when we update to obtain x2, then the next iteration would be solving this almost the same objective function, but subject to the penalty of lambda 2 times x minus x1. So the new anchor point becomes the previous iterate x1. So we're basically going to be finding the next iterate that is going down as far as possible, but not straying too far away from x1 here. And straying away from x1 basically can be represented by drawing a circle around x1. Any distance, any point along the circle, this circle is equal distance away from x1. And we want to go down, so we eventually would arrive at a point that is drawn here as x2. Same story goes. Next step, when we find x3, we will draw a circle around x2 and then find the point that is the best for the purpose of minimizing a naught times x. So notice that in this case, the identification of the solution iterates follows a different mechanism, which is basically still finding some kind of normal or tangential point between the a naught vector and the circles, but the circles now are moving circles where the centers are moving based on the solution iterates. It just so happened that, for example, in this particular case, the very simple case of Euclidean uncertainty set that became Euclidean norm penalty. In this particular case, in the linear objective function, a naught times x. In this particular case, the way that the a naught vectors are normal to the concentric circles, they actually happen to be aligned with the ways that the a vectors, a naught vectors are normal to the not the concentric circle, but to the moving circles on the right hand side. So in a way, the three things are normal or tangential at the same time. These moving circles, the concentric circles, and the a naught direction. So this is a case. Sorry, this is just to say that this is a case where so even though the two different forms of optimization problems are different, one is anchoring x at 0 each time, one is anchoring x at x k minus 1. But under some conditions, we can see that this is probably the very clean condition simple condition. We can see the two different solution sets can be the same. And so, and the intuition would generalize, or we can change the simple two norm or Euclidean uncertainty set to be general convex uncertainty set, following what we define as growing the uncertainty set around E naught by the radius r. And the unbounded feasible region, we can consider a more general convex feasible region. In which case, some feasible regions would lead to the two paths, the robust path and the optimization path, to be the same or to coincide. But some other cases, the general convex feasible region, we would see a gap between the two different paths. Our results would sharply quantify the gap between the two paths. In terms of the objective function, we can relax that to be convex in x and concave in a, and that would induce most likely induce a gap between the two different paths. Okay, so maybe we can very quickly go through this if time allows, very quickly go through the more general intuition, which is to say that, and sorry about the switch in notation as we go into the more general notation here, but again, so this is often is that's centered around A naught and growing by R. And in this case, we can take the shape of the uncertainty set. This V here was the B that I used earlier. Take that and take the polar of that and then form the regularizer term. But we take the polar of the uncertainty set shape and also compose it to make it smooth and strictly convex so that we have uniqueness of solutions and so on to allow us to have nice analysis. Right. So basically the phi here is, or the phi here is the distance generating function that we can then use to define our Bragman divergence. So that's a precise mechanism that we use here, and this problem that is the reformulation of the robust problem can be related to two other solution sets. One is the proximal optimization path. The other one is the intermediate object that we need for the analysis, which is a central path like object, and they're very similar in the sense that these three solution sets can all be written as a way of starting from some point and then going forward in the direction of A naught, and then mapping that solution back into the feasible region, and also jumping through the gradient mapping of the distance generating function and a dual of that. And so the form aside, the similarity between the three different solution sets is that they have similar forms, but then they start from different starting points, and that's a basis of our analysis. And our analysis is saying that okay, so I talked about when X is unconstrained. If X is constrained but has a nice feasible region, we still could have the two solutions paths, the robust path and the algorithmic optimization path, to coincide. Case one is if the feasible region is a simplex, and the I think the uncertainty set is Euclidean, then we would still have the coincidence of the two paths. Or if the feasible region and the uncertainty set are dual or polar of each other, that can also allow us to have the two solution sets to coincide. Okay, so that is a more general description of what I just said. But visualizing that, right? So if the blue dashed line is the robust path, and then the black dotted line is the optimization path, they would coincide in the unbounded or a hyperplane case, X feasible region is a hyperplane, and or if the feasible region is a simplex, but numerically we see that and we visualize that these two paths are not exactly the same when the feasible region becomes more complex. Right? So this is saying that in this case, the simplex is a sharp boundary of whether the two paths would coincide. And in general, we can quantify the difference between the two paths as measured by comparing two representative points from the two paths correspondingly. And so numerically, we can look at the following case. Let's say we have an uncertainty. Let's say we're doing a portfolio optimization problem. We're trying to invest into a collection of, let's say, stocks. So we have n stocks to choose from. We have, let's say, a budget of 1 to be allocated to the different stocks, facing a risk that is described by the covariance matrix of the return. the volatile or the random return over time. Um, and um, um, and then there's a conservatism level alpha that we can tune to sweep between the maximum return versus maximum risk portfolios. Okay, so this is the typical classical setup. In this case, we because the feasible region is a simplex and the uncertainty set is a ellipsoidal shape, our theory predicts that the robust path and the optimization path would coincide. And numerically, we do see that the in-sample, for example, the in-sample performance, they do coincide up to the sort of discretization error of jumping from one solution iterate to the next. And because they are the same solutions, it's easy to um, presume that they should also perform the same if we use out of sample data to test. If we add additional constraints to break the feasibility, to break the simplex feasible region setup, right, to have a more complex feasible region that's related to the different transaction um, condition or realities, then we see that the optimization path no longer um, traces the robust path, which is the right one. And this is the in-sample performance. That's where we do the optimization on. And then the out-of-sample testing, because the two different solution paths are different, they would give us there's going to be discrepancy between the solution performance in that different two different objectives, measuring the return and risk under the new data set, out of sample data set. In another numerical experiment, when we look at training a adversarial machine learning problem or solving for the model parameters of an image classification model, subject to an adversarial attack on the feature parameters of the data, which are in this case pixel values of the images. And the goal is to classify them into one of the 10 categories as accurately as possible. Now, so in this setup, this is probably very far away from what our theory can predict because, for one thing, the objective function is not linear and is not concave convex. It's highly nonlinear for a neural network loss function. So, so our theory doesn't really say anything here anymore. But we still wanted to check what would happen. I'm still curious. And also, we were not exactly solving the proximal point, customized proximal point method anymore. We're using the several different crude approximations of that, sometimes more crude. For example, stochastic gradient descent would be less accurate, which is basically assuming the proximal term to be to have the Euclidean shape. But nonetheless, we can run different solution algorithms and see how they compare with the actual best solutions in if we had solved the problem many times individually by changing the uncertainty set size. So what we obtain is that the red line is the solution, a set of solution performances from the robust solutions, and these measured in the clean accuracy and adversarial accuracy, and then so they correspond to different attack strengths, and the other lines, the dashed lines, they correspond to the solution paths that we obtain from using the different solution algorithms. And so we see very interesting phenomena. But just to point out briefly here that obtaining each adversarial machine learning model solution, training one adversarial machine learning model, naively would take about 15 minutes each. But the solution algorithm actually would only take about 15 seconds for each iterate that we obtain. Again, this is not visualizing the solution space. It's high dimension, very high dimensional solution space. For illustration, for the purpose of presenting, we are illustrating on these two different metrics: nominal accuracy and adversarial accuracy. Similarly, as we defined the efficiency metric and the robustness metric. Okay, so two things to point out. One is that in many of the figures, for all of them, we see that the algorithm, the solution, the optimization path actually perform better in a way. Pareto dominate the robust solution performance. We don't have a conclusive statement about this, but this could be at least from two different two independent different reasons. One is that the robust solution, as we said in the nonlinear objective function, they may not be Pareto optimal in this two objective space. So it is entirely possible that the algorithm solutions actually found better solutions that are actually closer to the actual Pareto optimal frontier in this space. Right? And of course, there are other different metrics we can use, but at least in this space, the solution, the algorithmic solution may be closer to the Pareto optimal. That's one. So there's a gap between the robust front and then the Pareto front that we are exploiting heuristically with the algorithmic path. The other possibility is that it may be that the true robust path, the true robust front, they are close to they are the Pareto front, but the numerical solution of these robust solutions and the solution front is not precise due to the underlying nonlinearity in the objective function. That's another potential reason. But nonetheless, in either way, we see that the optimization path would give us better solutions than individually solving these robust adversarial problems. So good that it is both the algorithmic solutions are better in terms of quality as well as faster in terms of the time to obtain each one of them, at least for the first segment, and at least for the two objectives that we defined here. And in the middle, if we actually restart the algorithm, we can see that the solution path can actually recover. The algorithmic solution path can actually recover in terms of the performance, doing better in both clean accuracy and then the adversarial accuracy compared with not restarting. And this is probably, I don't know, this could be due to the aggregation of deviation along the algorithmic path. When we run the solution path for long enough, it's going to deviate from the robust path. So with that, I would like to conclude the talk, and thank you very much for your attention.